You all know that without an atmosphere we cannot survive. But do you know what our atmosphere actually does for us? What every single layer does? Let's talk about it. Hey guys, welcome to Geo Amplified, and in this video we are going to be looking at the Earth's atmosphere. We're going to be looking at the structure, the layers, everything that each layer does for the survival of all of us on Earth. Let's get into it. So looking at the Earth's atmosphere, we can see the bottom layer, which is the troposphere. So now the troposphere is approximately 8 kilometers thick at the poles and 17 kilometers thick around the equator. And it contains most of the air of the atmosphere. It contains the gases that are essential for life, like nitrogen, oxygen, even carbon dioxide, which is needed for life. I mean, trees taking carbon dioxide and emit oxygen. So for them to live, they need carbon dioxide. In addition, the behavior of the air in the troposphere leads to weather, wind, rain, temperature changes. Everything happens within the troposphere. Then now going above the troposphere, we're going up to the stratosphere. Now the stratosphere is the second layer above the Earth's surface, and it contains something very important which we call the ozone layer. So now the ozone layer is made up of a gas called O3. So O3, which is ozone, right, is made up of 3 oxygen molecules. So now what these molecules do is they absorb all of the sun's harmful UV rays. They only allow a certain amount in. Think of it like a sponge. A sponge can only absorb so much before it starts to drip out. But now, will you get more wet if there is a sponge above you absorbing a lot of the water and you get just trickled on? Or if we remove the sponge completely and it just pours onto you, when will you get more wet? You'll get more wet when there is no sponge. So, looking now at UV rays, if there was no ozone layer, all of this harmful sun's UV rays would come through that part of the stratosphere and they would come and hit us, right? You would literally become Kentucky Fried Chicken. So that is what the stratosphere is. Stratosphere has the ozone layer, and that is important for our survival. Then we go one layer higher and we get to the mesosphere. So now the mesosphere is really cool. This layer is really cold, right? It's one of the coldest layers we have. And what the mesosphere then does is it prevents any dust, space dust, meteorites, rocks, anything from outer space getting into our lower atmosphere. It prevents meteorites from falling down. So what happens is in the mesosphere is a meteorite would come down, right? And as it goes through the mesosphere, it starts to break up. It starts to destroy itself, burn up. Right? So by the time it gets to the troposphere or stratosphere, it is just smaller pieces. So like those meteorites that land onto the Earth's surface, right? They are smaller pieces in comparison to what the actual meteorite looked like. So now looking at all that dust, that space rock and gases and everything, we get something that is called the Aurora Borealis. So now the Aurora Borealis is commonly known as the Northern Lights. And this is what happens when the sunlight mixes with the gases and the rocks and everything. You get a reaction that emits a kind of light, right? This light can be best seen in the Northern Hemisphere by Iceland, Norway, Slovenia, I think. And in the Southern Hemisphere, you also get the Southern Lights, and that can be seen in Antarctica. So these are the Northern Lights, the Aurora Borealis, and it is a reaction from the gases, the dust, the rocks, everything, and the sunlight and the heat, right? It has a chemical reaction and it creates this kind of light. Then we get something that is called the Kármán line. Now, the Kármán line is just above the mesosphere and just between the thermosphere. So now the Kármán line is an imaginary line that distinguishes our lower atmosphere to essentially outer space. So when they shoot up satellites, rockets, spaceships, whatever, as soon as it gets past the Kármán line, it is by definition out of the Earth's atmosphere, right? That is why now when we go to the thermosphere, so now the thermosphere it's the layers furthest from the Earth, okay, excluding the exosphere. Now the exosphere is outer space. So the thermosphere is the furthest layer part of our atmosphere, right? It is the extended part of our atmosphere, right? It absorbs a lot of the sun's harmful X-rays and ultraviolet rays. This is why the temperature in this layer is so hot. So the sun comes in, and as it goes, it hits this layer and it heats it up, right? So this layer is designed to absorb a lot of the radiation, but it doesn't absorb enough. That is why we have the ozone layer as well. So we have got a second line of defense, which is the ozone layer, right? This absorbs a lot of it. The ozone layer takes the last bit that we need for comfortable living. In the thermosphere, you also have your satellites. So this is the perfect layer for everything to revolve around the Earth. So once you hit past the common line, you are in, by definition, space, right? But you are not far enough to leave the Earth's gravitational pull. That is where the exobase comes into play. So the exobase, what it is it is the imaginary line that if you leave that line and you have enough velocity, you have then left the Earth's gravitational pull, which means you will carry on going into outer space. You carry on going to infinity. So if, for example, I am leaving the exobase at a rate of 1 kilometer per hour, right? 1 kilometer per hour, I mean, you can walk faster than that if you really had to, right? So if you are leaving at 1 kilometer per hour, you will keep going. Why? Because there is no friction. There's no particles, there's no other objects or anything that you can create friction from, right, to slow you down. That is why if you start sliding across the floor, why do you stop? Because there's one, gravity pulling you against it, and friction between you and the floor, right? So it creates a somewhat of a slowing of your movement, right? But in outer space, if you're going at 1 kilometer per hour, you will keep going forever and ever until you either get pulled into another planet's gravitational pull that can either speed you up or you'll crash into their planet, or you could be hit by dust particles, meteorites, asteroids, so on like that, or even hit into a rocket or something that was left in outer space. Who knows? But once you drift off, you carry on going. Right? Then we get to the exospheres. Now the exosphere, you can see the man in the rocket there, right? The exosphere is outer space. Once you have hit the exosphere, you are in outer space. So the exosphere, by definition, is space. So the question for today is as follows. Why is the sky blue? Think about it. Why, when you look up on a sunny day, you look up at the sky and it is blue? Let's do an experiment to explain that. Right, so all you're going to need is you're going to need to fill up the basin with water, and it can be hot or cold, up to you. Then you take the bar of soap, preferably a white bar of soap. It can be Dove, whatever, as long as it is a white bar of soap. Then lightly wash the bar of soap in the water to get a bit of that soap off into the water. You can wash your hands and just rinse your hands off in that basin, and that would be perfectly fine. You are then just going to take a glass and you're going to fill up the glass, let's say about just past halfway, maybe 3/4, with this soapy water that you now have in your basin. And that will then be the simulation of your atmosphere. Right, so this is the experiment. We have our light source, which is our sun, in this case the torch, and we have our atmosphere in a glass. Now the water is the atmosphere, and the soap bubbles and the soap pieces and soap particles inside are the dust particles and everything that is in our atmosphere, right? So you'll see the light, it's quite bright, it's a bright white light, and as soon as it hits the water, right, you'll see it changes blue. Now this is because the light that comes off is reflected from the light source off the particles to our eyes, right? So you see as the light goes over, it turns blue. This is to show what the sky looks like when sunlight hits all the particles and is reflected to our eyes. It is a gray water, and as soon as the light goes over, it turns blue. Hey guys, if you enjoyed that video, please leave a like and a comment, subscribe and hit that notifications button if you want to see more videos. Leave a comment with any suggestions if you would like another question, like for example, why is the sky blue? And I will explain it to you and do a demonstration or an experiment to show you why it is the way it is. So yes, please leave a comment and like, and we'll see you next time, guys.